This video is part of a series on the xv6 operating system kernel. In this video, I'll be talking about inodes. I'll talk about how they are represented and how they are stored in an array on the disk, and I'll be talking about how they are represented in memory. We have a cache in memory of the inodes that we're currently using. I'll go over some definitions from the files fs.h and file.h, and then I'll look at the code in fs.c. There are a lot of functions, 25 functions, in this file, and in this video I will just do an overview of these functions. I will actually walk through the code of these functions in the next video. Okay, let's get started. Previously I presented this picture, which is a schematic showing the layout of the disk. In this picture, each one of these small squares represents a disk block. And we see the area where the log is kept, that's here. We see the area where the inode array is kept, and that's here. We also have a bitmap, which is kept here. And we have the data block area. The data block area contains the blocks that store the data of the regular files and the directories. In the bitmap, there's a single bit for each one of these blocks, and that bit tells whether the block is free or in use. The blocks from 0 all the way up to here are considered to be in use. So within the bitmap, the bits corresponding to these blocks will be a 1 to indicate that those blocks are in use. Whenever we want to get a free block to add to a directory or file, we will look in the bitmap, and it will only find a free block somewhere in this area. Okay, next what I want to do is take a closer look at what's going on with the inodes. So here I am showing the disk again. Here's the log, here's the bitmap, here are the data blocks. This area is where the inode array is kept, and it starts at some particular block number, and that value is in the superblock. So there's a field in the superblock structure called inode start that allows us to find where this array begins. This array contains a number of structures. Each element in the array is an inode structure, and I'll talk about those in a second. They are packed together as tightly as possible. I'm indicating that we can get 4 of these structures per block. And here's a block right here, and here's a block, and each one of these is a block containing 4 inode structures with a little bit of wasted space at the end. There will be wasted space if we cannot get an even number of inodes packed into a block. And in reality, these inodes are not quite that big, so we can actually get more than just 4. But here I'm showing you that they are packed together like this with some unused space. Now let's take a look at one particular inode and see what that structure looks like. So I covered this before, but let me remind you that it has a type field that tells whether it's a regular file, a directory, or a device. If it's device, it's got a major number and a minor number. And in any case, regardless of what kind of file it is, we have nlink, which is the number of hard links that point to it. So if this particular file is in, let's say 4 directories, then the nlink will be 4. This tells how many directories point to this particular file. If it is a regular file or a directory, then it will have a size. The device files, we ignore the size and this array down here. And finally, for regular files and directories, we have to have the actual data. And so we have an array here of block numbers. Each block number can be thought of as a pointer to a block up in this data area here. And that array has a fixed size, which happens to be 12. So we have 12 blocks here from 0 to 11. And beyond that, if the file grows beyond a size of 12 blocks, what we do is we use an indirect block. So the next pointer, okay, the 13th pointer, points to another block on disk somewhere in here, and that block is filled with block numbers or pointers to other blocks. And since the block number is 4 bytes and the block size is 1024, we can pack in 256 pointers into the indirect block. So with the 256 blocks that are pointed to by the indirect block and these 12 blocks, that imposes the maximum size on any file. It's rather limited in xv6. Here it's given by these two constants. The number of direct pointers is 12, and the number of pointers we can squeeze into an indirect block is 256. In production Unix and Linux systems, we have other ways of accommodating bigger files. For example, we might have a pointer that points to a double indirect block. So each of these pointers points to an indirect block. It points to the block itself. We can also have triple indirection. And with that, we have a potential maximum file size that's absolutely huge. But xv6 just has this single block of indirection, and that's good enough for us. So we don't actually store the inode number. That's implicit. So this is the inode for file number 6. And we will then need to read it into memory where we can work on it. And for that, we have a cache of inodes that are stored in memory. So there's an array, or I should say a variable, called itable. That's a structure, and it contains two fields, a lock and an array called inode. And that array contains a number of structures that look like this. And it's fixed to have a size of 50, so we have up to 50 inodes out of the 200 that we can be actively working on. So if we are working on a file, that is, it's open and we're accessing it, what the kernel will do is it will read the structure from the disk into one of these cached structures. The cached inode contains all the fields that are in the inode on disk: type, major, minor, inlink, size, and the address array; type, major, minor, inlink, size, and the address array, as well as some additional fields. For one thing, we need the I number, as well as the device number. In xv6, we only have one device that can contain file systems, but in other Unix systems, we will have several devices that are currently being used. So in order to identify the file, we need not only the device number, but the I number. The I numbers are unique on each file system, but if we have several file systems, the I numbers, we could have some confusion, because I number 6 just says it's I number 6. It doesn't say which file system that's in. So it could be either this file system or some other file system. So that's why we have the device number here. The reference count is the number of pointers to this structure, or you can think of it as the number of threads that are currently using this cached inode. Within this cache of 50 inodes, the reference number will tell which ones are free and which ones are in use. If the reference number is 0, then it's free and it can be used to cache a different inode. But if it's in use, the reference number will be something greater than 0. The structure also contains a lock. Oh, I've labeled these wrong. The lock field is a sleep lock, okay, and the valid field is a flag. And the sleep lock protects this. So whenever the kernel wants to read or update any of the fields in the inode, it must be holding the sleep lock called lock. At some point, the particular element in the cache is allocated to some inode, and the I number is filled in, along with the device and the reference count. But the data may not be read in immediately. So the valid flag tells whether the data has been read in from disk or not. And if it's 0, then we need to go ahead and read in from disk if we're going to look at it. The fields up here, the device number, inode number, and reference count, are protected by a spin lock in this itable structure. And that spin lock protects all of these. So when we allocate an element from the cache to be used for a particular inode, we will need to first grab the spin lock and then set the I number and the device, as well as incrementing the reference count to 1. There's another variable called device switch, and that's an array. It happens to be containing 10 elements, as given by this constant number of devices. Each element in the array is a structure, and I've shown one of them enlarged here. And for each device, there is an element in this array. And what does the array contain? Well, it contains pointers to functions. So, for example, element number 1 is the console. Whenever we do a read or write to the serial output, we need to access this device. And so for the console device, we use these two particular functions to perform the read and the write. For other devices, we might have different functions. So these are essentially the device drivers that are specific to device number 1. So for the console device, the read function takes a destination address. This is a buffer in kernel memory where, well, it's a buffer where we're going to be storing the characters that we read. Here we have a byte count. That's how many characters we want to read. And here we have a flag. The first argument is either 0 or 1 to indicate whether this destination address is a physical address in kernel address space or whether it's a virtual address in some user's virtual address. And it returns the number of bytes that we have successfully read. Likewise, there's a console write function. It takes the address of where the characters are and how many bytes there are that we want to write out to the console, as well as a flag to tell whether this address is in the kernel space or the user's virtual address space, and it returns the number of bytes written. In xv6, this array is not really used very much. In fact, the only element that has anything in it is device number 1, and so that's the console device. It's a bit confusing because the file system is also on device number 1, but that's just the way it is. So we're only using this device array for the console. But here you get the idea that for different kinds of devices, we could have different routines to be used for them. So the major number would be used to index into this device to tell us which functions to use. And the minor number would probably be passed to the driver to indicate which device to send it to. Now let's take a look at the file fs.h. In the real world, there are several kinds of file systems that are in common use, and here's some examples. ext4, the file system used by Minix, xfs are some common ones. We might call the file system format used by xv6 fs. A real operating system is going to need to be able to handle several different file system formats. xv6 can only handle one, and the definitions that are related to the on-disk file system formatting are contained in this file fs.h. So let's go through and see what it's got. First of all, we need to be able to locate the root directory, and that is inode number 1. The block size for the blocks on this disk is 1024. The second block, that is block number 1, is the super block. It's a block that's read in at startup, and it contains a number of values, and these values never change, and this block is never updated. This just basically tells us where the log and the bitmap and the inode array are on the disk. Here's the magic number that's related to this field. Inodes contain 12 direct pointers. Okay, that's this number here. And the indirect block will contain a number of pointers given by this constant here. We take the block size and divide it by the size of a block number. And that's the 256 number I referred to earlier. The files have a maximum size determined by the number of direct pointers plus the number of indirect pointers. So that's 12 plus 256. And given that the block size is 1024 bytes, that imposes a maximum size on every block. The inode, as it's kept on disk, has this structure here, the type, the major and minor numbers, the number of hard links, the size in bytes, and this array with 12 direct pointers and 1 indirect block, which is pointed to by the 13th element in this array. Let's go to the next page, which is here. This constant here is the number of inodes we can squeeze into one block. Okay, here I indicated it was 4, and maybe the block size is evenly divisible by the size of the inode structure, or maybe it's not, in which case we have a little bit of extra space. But in any case, it's not really 4. It's given by this inodes per block value here that is determined by the size of the block and the size of the inode structure. Okay, which block on disk will contain a particular inode? So this function, this macro preprocessor function, iblock, is passed an inode number and a pointer to the superblock, which is a structure in memory that has things like where the inode array starts. In my example, I started it at 32. And so we just do a little bit of division here by the inodes per block and add 32. The bitmap will contain a number of bits in each block, and the number of bits in each block is just 1024 bytes times 8 bits per byte. So given a particular bit number or block number, which block in the bitmap will contain that bit? Okay, so B is the block number, and this B block will compute B divided by the number of bits per block and where the bitmap starts. The directory contains a bunch of files, and each file can have up to 14 characters in its name, and so that's directory size here. And the directories will contain a number of these directory entries, which has, each one of these structures has an inode number and 14 characters, so it can accommodate a file name size up to 14. Okay, now I also want to take a look in this file, file.h, which contains a number of different things, but in particular it contains the in-memory inode. So remember that our cache is made up of 50, it turns out to be 50, of these inode structures. And we have the fields that I talked about in this picture here. So here is the structure, as I showed it before, device, inode number, and the reference count. So device, inode number, and the reference count. And then we have a sleep block, and here's the sleep block called lock. And this sleep block protects everything below that. Okay, so we have the type, major, minor, in like, the number of hard links, size, and the pointers. It also protects the valid field. I didn't really draw this quite correctly, but the sleep block corrects the valid flag as well. And then I mentioned the device switch array, and that's given right here. These are the structures, and each one is a structure that contains 2 pointers, a read and a write field. So that's was shown in this picture here. This structure here contains 2 fields called read and write, and each of these is a pointer to a function. Okay, the function takes 3 arguments and returns an integer value, and the array itself is declared elsewhere. Okay, that's it for. Oh wait, we also have this console, which is the number in the array of the console device. There are a couple of other definitions that I wanted to cover, and these are coming out of the file fs.c, not .h. Here is the superblock variable, sb, where the superblock is read into at startup time. Then we have a macro function called minimum, which is defined pretty much as you would expect it to be. Remember that as a kernel programmer, you have to define everything you're going to use. You can't rely on library functions that you would normally rely on as a regular programmer. There's something else that I wanted to mention, and that's the itable structure. Here is the picture of it that I used. This is where we have the cache of inodes, and it has a spin lock, and it has this array of inode structures that we will use as our cache. And I also wanted to mention something from the file.c, and that is this array I discussed previously called device switch, which has 10, as it turns out, elements. I won't talk about the rest of this stuff right now, but I'll cover this in a later video. There are a lot of functions in fs.c. In fact, there are about 25 functions. The code in some of these functions is pretty complicated, and before I get into the code itself, I want to just introduce these functions by name and talk a little bit about each one of them. The first 3 functions are concerned with initialization. init is for initializing the cache of inodes. File system init is past the device number, and it initializes things, and among other things, it calls read SB, which will read in the super block from the disk and store it in this super block structure. The function B0 is passed a block number, and it will go out to disk and write all zeros to that block. balloc is used when we need to allocate a block, for example, when we're growing a file. And so it will search the bitmap to find a block that is currently free, and it will change the bitmap to indicate that it's now in use and return the number of that block. To free the block after we're done with it, we can call bfree, which is passed a block number, and it will change the bit in the bitmap to indicate that the block is now free. The ialloc function is used when we're creating a new file, and we say which device we want to create it on, and the type of the new file. This could be a regular file, a directory, or a device file. And it returns a pointer to the inode, that is to a structure in the inode cache. What it will do is it will read the disk to locate an unused inode in the inode array. And so at that point, it determines what the I number of the new file will be. Remember that the inodes in this array will have a type value of 0 to indicate that they're free. And so this function will set the type on the disk to indicate that that inode is now used. And then it will call iget and return a pointer to the inode. And so what does iget do? Well, at this point, we've got the I number of the new file, and we allocate a structure in the inode cache. Okay, if we already have a structure for that particular I number, then we go ahead and use that one. But in either case, we increment the reference count to indicate that this particular inode in the cache is in use. We will not actually read in the inode data from the disk. Okay, remember there's a valid flag in the inode structure, and so that may remain 0 to indicate that there's no valid data. And each inode in the cache has a lock associated with it, and iget will not set the lock. Okay, if we want to set the lock, we can call ilock, which is past a pointer to the inode, and it will set the sleep lock in the inode. Furthermore, if the data in that node has not yet been read in from disk, then the valid flag will be false or 0, and this function will also read in the data from the inode structure on disk and store it in the cached version. And there is an unlock function which will simply unlock the inode. Next, we look at the iUpdate function, and this is passed a pointer to an inode in the inode cache. And after we've made changes to the inode, we need to write that inode back to disk, and that's what this function will do. From time to time, we need to increment the reference count, and so we can call idupe to increment that reference count. Remember that the reference count is protected by the lock for the entire cache, the itable.lock field. So it'll have to set that in order to increment the reference count. And the iPut function is passed a pointer to an inode, and it will decrement the reference count. Now, if this particular thread is the last thread that's using that inode in the cache, then the reference count will have gone to 0. And at that point, we can also ask, or this function will also ask, whether there are any hard links to this file. And if inlink is 0, it means there are no references to this file from any directory. So at that point, this file is not accessible. There is no path name which can get to it. So this file needs to be released and freed. The space associated with it has to be freed. So what it will do in that case is lock the inode, truncate the file to a length of 0, which will free all the data blocks, and then it will call this iUpdate function here to write the modified inode back to disk. and at that point the file is freed. The function iUnlockPut is just calling iUnlock followed by iPut. And then we have this bmap function. It's passed a pointer to an inode, so we've got some file that we're concerned about, and we've got the inode cached in the inode cache. And we are trying to get some data out of the file, or perhaps write data into the file. So we figure out which block in the file, with the first byte of the file being in block 0 of that file. So we have the block number relative to the beginning of the file, and we need to translate it to a block on the disk, and that's what bmap does. So it will consult the array of block pointers, of direct block pointers, and if it is a block beyond the 12th block, it will look at the block of indirection, and it will find a pointer to locate the block on the disk. So it will figure out the block number on the disk. If that block is not actually allocated in the file, okay, it's not in the file, then this function will also allocate a free block and add it to the file, and it will also update the inode by adding it to either the array of direct pointers or the block of indirect pointers. Next, let's look at the function iTruncate, which has passed a pointer to an inode, which is in the inode cache. And it will truncate this file to size 0. It will free all the data blocks in this file, and it will free the indirection block too, if there is one, and set the size attribute to 0, and call iUpdate to update the inode on the disk. This is called, among other places, from the iPut function. Remember, with iPut, we basically call this when we're done with a particular file, and it will decrement the reference count. And if there are no hard links to it, then it will truncate the file to length 0. It calls iUpdate as well as iTruncate, and you might think, well, gee, that is a duplication of effort. It's writing to the disk twice. But remember, we're using the disk logging system, and so there will only actually be one write to the disk. The reason we call iUpdate here a second time is because we are also setting the type field to 0, which I did not include in this. So let's add that there. And we need to set the type field to 0 and then write that to the disk so that the on-disk inode structure will have a type of 0, which will indicate that this particular inode is free and can be recycled. Okay, the next function is stat_i, and this is passed a pointer to an inode and to a structure called a stat structure, and all it's going to do is copy data from the inode to someplace else. Now we want to look at the read_i and write_i functions. These are used to actually move data into or out of a file. So read_i is called with a pointer to an inode that's in the cache and a destination address of where to put the data in memory, as well as an offset in the file of where to get the data and the number of bytes to transfer. This destination address is either a physical address or it is a virtual address in some user's virtual address space, and that's determined by this flag. 0 if destination address is a physical address, 1 if it's a virtual address, and it'll return the number of bytes read. The write_i is just the other direction, and here we have the same arguments, a pointer to an inode, the flag, the source from where we're getting the data, and the number of bytes, and where in the file we will be writing it to, and then it returns the number of bytes correctly written. And then we have the function directory lookup, and this is passed a pointer to an inode. Okay, that's a directory file, or at least it should be a directory file, and a name. Okay, this is something that's 14 characters or fewer, and we also have an offset variable, and we'll pass the address of that. So what it's going to do is it's look this name up in the file that's pointed to by this inode here. And if we find this name in the directory, then we're going to call iget, which will add an inode for this file into the inode cache. It will not lock it, okay? And it will then return the inode of the file that we just looked up. In addition, we've got this offset variable, and so this function will also save the offset in the directory of the directory entry for this particular file. So it will save the location of this directory entry within the directory array, the directory file, in this variable offset. And if the file is not found, it will return 0. The next function to look at is directory link, which is used to add an entry to a directory. So it's passed a pointer to an inode that represents the directory, as well as a pointer to a name and the inumber, and it will add a name-number pair to this file. It will return 0 if everything went okay, and -1 if there's a failure. And the failure can happen if there is already an entry for that name in the directory. And this function will do reads from the disk as necessary to check, and after it adds the entry, it will write that back to the disk. By the way, all of these functions that we've talked about so far are reading from the disk, and many of them are writing as well with a log write operation. These reads and the corresponding writes and the releases, the B release function calls, are all part of transactions, but none of these functions include the transaction itself. Remember, the transaction begins with a call to the begin op function and ends with a call to the end op function. None of these functions in fs.c, in the file fs.c, contain calls to begin op or end op, but they are all used within code that is part of a transaction. The next function, skip element, is not a function that accesses the disk. It doesn't do any reading or writing. It's simply a string processing function. It's passed a pointer to a path name string somewhere in memory, such as this string right here. And so it's passed a pointer to the first character. And it will parse it, essentially. It will find where the first element is, and it will store that in a variable called name. So it's passed an address of some 14-byte area, and it will store whatever the first element in this path name is, and in this case it's the characters USR, in the name variable. And it will also advance the pointer to the next element in the path name and return a pointer to the next element. So it will return a pointer to this. If the path name is empty and there are no more elements, it will return 0. Okay, finally we have this name I function, and this is what we've sort of been working toward. We're passed a pointer to a path name, and it's going to find that file on disk, move the inode into the inode cache, and return a pointer to the cached inode. So the inode will be cached, and the reference count of that inode will be incremented. It will not be locked, and if the file doesn't exist, if this path name is no good, then this function will return null or 0. There's also a variation of this that will do exactly the same thing. It's passed a pointer to a path name, and it returns a pointer to the inode in the cache, but it will stop one level earlier. So basically, if it's passed this path name here, it would return a pointer to the directory user/bin, okay, and it will save cat in this name variable. So it'll stop one level earlier in the path name, save the last file name, that is cat, in this name variable, and it will return the inode of the parent directory. And both of these are quite similar, and all they do is call the function namex, which actually does the work of both the name I and the name I parent function. So namex is passed a pointer to a path name and a flag to tell whether it's doing the name I function or the name I parent function. and the name variable. And it does the work of both name_i and name_i parent. And name_x is not called from anywhere else. Okay, that's it for this video. In the next video, I will start looking at the code for these functions. See you there.